They teach that up there then.
Okay. You're ready to take a walk. Alright, so I guess let's get started. Thank you. So I continued looking at the subtropical South Atlantic, the circulation there, and I made some estimates of the mean flow, and now I'm going to expand on this a little bit to go into the variability using the same product as before, but I extended the time period. Okay. This is supposed to go forward and that's here, but it's not. Okay. So let's try the old-fashioned way. There we go. So with this velocity field that I generated, I wanted to see how well it can produce the variability of the transporting subtropical gyre. And then I want to look at how the gyre varies over time, and then what can we learn about the sourcing of this variability. So that's going to be relatively short, the last part, but I'm going to talk a little bit about that. Okay. So the data set, now I have 14 years of data from Argo flows. Now I have Argo and both trajectories going into February 2014 now. I have the T-process height from Aviso, unfortunately only going to August 2013, but I will update that soon. Then I have the wind field from CCMP that I looked at. I'm not going to show any of those, but I compared them to the other wind fields. I had the wind field from EI interim, which is the ones I'm going to show actually, and I had the wind field from the interview analysis too. And I only chose the EI interim over the CCMP basically because the time series is longer. So some people have seen this, or everybody has seen this slide before. Basically, I'm deriving the dynamic height using the sea surface height from Aviso and the density or the Argo data to get the dynamic height in situ. And then I correlate the two, and then I use that to get a dynamic height field, three-dimensional, so latitude, longitude, depth, and then monthly fields for the whole time period from 2000 to August 2013. And so this is an example of what the velocity field looks like. In the lower left is the 20 decibel depth velocity field of the zonal velocity from geostrophy using that synthetic altimetry derived dynamic height fields. Then on the top right is the reference velocity from the subsurface trajectories of the Argo flows and the Wolf flows. And then on the bottom right is the absolute velocity for the geostrophic plus the barotropic component from the subsurface velocity field. And the main difference we see is that pretty large differences in the southern South Atlantic, where the circumpolar current is at the very southern edge of the picture, and the South Atlantic current just to the north of it, that adjusting that velocity field gives you a lot higher velocities near the surface. So that's good news because the currents are too weak on the left, and then they are not better on the right. So anyway, so this is the unadjusted field. And we also see a little bit higher velocities in the westward flow here. Well, get a little higher. So the reference velocity comes from the subsurface trajectories from Argo flows and other flows that are available to me.
Are you processing them yourself, or are you using one of the many products?
I'm processing the subsurface trajectories myself. So then you have control over how much everything gets smoothed and things like that, and how the data gets corrected for surface drift and all these little things. And this is an example basically for the Meridional velocity field, also for January 2011. And it's the same. This is the geostrophic velocity field relative to 1,000, and this is the adjusted geostrophic velocity field, which basically also shows a little bit higher velocities. For example, here in the boundary cones also you get higher velocities. So it's pretty good as far as I'm concerned. Now this is from a paper I had earlier, which basically shows the major cones. So the southern South Equatorial cone here, the South Atlantic cone here, just the northern edge of the circumpolar cone, then the Venezuela cone, and the Brazil cone here, and the Marinas cone coming in right over here. And I'm not going to say much about the northern areas here, so I'm focusing on subtropical gyre. And then, this one is 0 to 100 meters, and then without Ekman and with Ekman. And then this is 100 to 200, 200 to 400, 400 to 800, 800 to 1200, now to 1600, and 1600 to 2000. In this presentation, I'm going to focus primarily on the upper 800 meters. So this is a movie of the updated velocity field. I'm not sure how long I want to show this. So this is the zonal velocity at the top, and then the bottom shows the vector plot. And it's smoothed quite a bit, so you don't want too much noise. And it's basically going to cycle through, and I'm not going to wait until the end of 2013. So anyway, so this is the upper 400 meters. And it pretty consistently shows the subpolar gyre here. And it shows some variability in the Gunner's cone region, and some variability along the western boundary as well. Let me stop this one and go for the next one. And so this is the next layer. Using a little bit the same scale, I think in the top panel. Also, the top panel shows the zonal transport, and the lower panel is the vector of the transport. And so it's a little bit quieter, a little bit lower transport in that layer. So I'm going to stop this movie as well. Okay, that works. So then, in the earlier work, I calculated the mean transport along the western boundary. So in the 0 to 400, 400 to 800, 800 to 1200 meters. And in all these layers, I found the latitude dependence of the transport. So the upper 0 to 400 plus 400 to 800 would be the Brazil cone. And then below is not considered a Brazil cone anymore, but it goes in the same direction. So especially here where the intermediate waters joins the Brazil cone, you get higher transport.
So Claudia, the reference velocity that you use, is it also constant?
It is, and I will get to that later. Yes, but I don't have a full 14-year time series of the subsurface velocity at every grid point. No, I don't. So I have to use some tweaks. Anyway, so I'm going to tell you later how I'm going to get it. Yeah.
Do you get the outward transporting the about 24, 25 out below 400 meters? Or you get north?
I can go back if I just think close to me. Okay, no, I will.
So your earlier.
You mean if I get southward velocity?
No, transport. The transport you were showing.
Right, but velocity of transport, I mean, you mean at which depth?
Yeah, below 400. 400 to
And so there's a little bit of southward stuff here, but not very much. So, this is an old picture, so the new one has more data, so it will probably show up better. 75, I think. So this is a comparison of the 0 to 800 meter Brazil cone on the left with earlier results from various publications. And even though the Brazil cone is a bit tricky to get it from Argo data because you don't have data on the shelf or very close to the shelf, the transports agree really well down here where the Brazil cone is strong. And even up here they agree pretty well, with one exception right here. So, and these are just individual measurements from one cross-section, so the scatter is can be quite large. And also going to 2,000, some people estimate the transport down to 2,000 meters, even though it's not really for the cone anymore. It also agrees pretty well with earlier published results. And then I did the transport along the eastern boundary. For 0 to 800 is the more interesting one for the Benguela cone. And again, the results from this velocity field agree really well with earlier observations from various studies. And there's also a latitude dependence, but it's not as strong as for the Brazil cone. And then a South Atlantic cone. For the southern edge, I used the polar front based on a salinity of 34.9. And for the northern edge, I simply used the latitude where the velocity changes from eastward to westward. And then you get a longitude dependence of the transport, and you get a longitude dependence of the width of the cone also. And so this is the upper 400 meters, and the same happens in the 400 to 800 meters. They're pretty similar patterns in the transport. And so then for the southern South Equatorial cone, it kind of starts in the upper 400 meters relatively narrow, and then it becomes wider and wider. Now, defining this northern edge is a little bit tricky. The southern edge is the same as I used for the South Atlantic cone, but the northern edge is kind of difficult sometimes to find in the data. But most of the time I get a pretty good estimate. And so this scatter is actually from the full time series over almost 13 years. So you get some standard deviation here. And there is a longitude dependence for the transport, but it's mostly here in the eastern part, and it pretty much flattens out with some variability here. And the same pretty much is happening at 400 to 800 meters, but the cone is significantly narrower, which is typical for the subtropical gyre. And then this is from the paper as well. It's the overview over the zonal transports here, the westward transport here, eastward transport. And then there's this pretty strong northward transport here in the interior, which actually kind of sort of balances with the change in the westward transport and in the change of the eastward transport. And it does it both in these two layers, even here. Only in 2006, 1600 to 2000, that balance breaks down. Anyway, so there's a pretty strong interior northward flow in the subtropical gyre, and it's away from the eastern boundary. So this is from the study by Silvia Gazzoli and others in 2012, showing the Brazil cone transport from the XPT sections. Over here, this is at 35 south, these dots, and these are at 24 south. And then up here is the Benguela cone. And so, and then there are some estimates from Stromer in 1989 for 3 different cruises. They're also right in the ballpark here for 35 south, or close to 35 south, 32, 33. And so then I'm comparing what I'm getting at 35 south from this new velocity product, and it's a similar amplitude but a different magnitude, which is, I think, mainly how we define what is the Brazil cone. And in my product, I'm missing the westernmost part that is very close to the shelf break. So I'm not surprised that my transport at 35 south are a little bit smaller. And yeah, and then an agreement is that both large transports here in 2002, 2003, it's relatively large transport right here, and I have relatively large transports here around that 2000, end of 2002, beginning of 2003. And then in 2004 and 5, I have relatively small transports right here, and there are relatively small transports right here, most of them. There's one exception right here. So that's kind of confidence building in the data set. And so you may wonder what these white and black curves were. So now I'm getting into how I'm doing the subsurface velocity. I actually did it two ways. One is I used the mean subsurface velocity, so total climatology. No seasonal cycle, nothing. And that results at 38 cells for the Brazil curve and 0 to 800 meters in this curve here. If I use monthly mean subsurface velocities to do the adjustment, I get a stronger seasonal cycle. Now this is dependent on where you are. So here's a different example, South Atlantic current. You get both show a similar shape in the annual cycle, but the black one that uses the annual cycle of the subsurface velocity is a little bit stronger. And that's relatively typical what I see at other locations. So here's now looking at basically 4 curves of the subtropical gyre. So these are the boundary curves, so these curves in the west, and I did minus of the transport, so the curve is essentially upside down, so it's easier to compare the maximum and minima that way. And I did the same for the south and south equatorial curve here. I also used the negative of the transport. And so then I have basically here always the maximum minimum in which month they occur in those 4 plots. And essentially what happens here is that the south and south equatorial curve lags the Benguela curve by about 5 months. And the Brazil curve transport lags the south and south equatorial curve by 4 months. So basically this maximum here from the Brazil curve is in month 12, and here it's 8 to 9, so there's a 4 month offset. And then similar to the Benguela curve, well, the South Atlantic curve has a lag by about 5 months. And so this is kind of summarizing the previous one. So we get a 5 month lag here, we get a 4 month lag here, and we have a 5 month lag here. And these are indicating the lags, the lines in the same color code as up here. And then between the South Atlantic curve here and the Benguela curve, I don't get anything significant in terms of lag. But I'm not surprised about that because we also have the Marinas curve. So the Brazil curve alone will not explain how the transport here varies. And then for these, here the annual cycle is a lot, I mean I smoothed it a lot, but still the annual cycle is pretty stable for the South Atlantic curve and the South and South Equatorial curve for the 15 years almost. For the Benguela curve and for the Brazil curve, I get more noise, a less stable annual cycle, which is not surprising because the boundary curves are a little bit more difficult to estimate. And then here I'm looking at, I was actually looking at different indexes, and none of the indexes that I could find have anything to do with the variability I'm seeing when it comes to in the annual stuff. And for seasonal stuff, I don't think comparing some of these indices with this transport time series doesn't make any sense. Because every time series will have a seasonal cycle, so we'll always get some kind of correlation, but it doesn't mean anything. So what I'm looking at here together, let's start with the annual cycle first, is the transport at 30 west from the South Atlantic curve and the zonal wind stress, and from the EIA interim. And I find that the transport minimum and the wind stress minimum and maximum lead the transport minimum and maximum by about 2 months. Now we are in a subtropical gyre after all, so that's not surprising. It's wind-driven. But it's still quite nice. It significantly increases the confidence in my velocity field to have this pretty robust result. And here's the 4 time series. And you can see most of the time you see the very clear lag here, where the red curve is a little bit ahead of the blue curve in most of these years. Yes. Well, it didn't really make much difference what I used in that sense. I looked at both and I just decided to show only one. And so, and then in the south and south equatorial cone, I pretty much see the same 2 months lead here. So, and in the EIA 15, I have to look at it a little bit, EIA interim, why there is this weird thing here where the seasonal cycle seems to disappear, but then it comes back. But in the long-term mean annual cycle, it's pretty clear, the 2 months here. So, oh, I was too fast again, as always. So to summarize, the orthogonal current transport variability at 35,000 is similar amplitude in new estimates as reported earlier. The transport of the zonal and meridional currents in the subtropical gyre reveals significant seasonality, and some of this is due to the adjustment of the geostrophic velocity. So it basically amplifies in many locations the seasonal cycle a little bit. Then the comparison of the time series of the currents at 4 locations show reasonable lags between each other. And then the final one was the transport of the zonal currents at 30 west lag about 2 months behind the zonal wind stress at that longitude. And so these are the main results from what I prepared for this. So if you have any questions? Yes?
Have you by any chance looked at the relationships and how they change if you filter out the annual cycle and focus on the interannual?
I started looking at that, and I still have quite a bit of work ahead of me. So yes, that's absolutely something I want to look at. Any other questions?
Yes,